It's a great pleasure to introduce Erik Meijer, who runs Cloud Programmability team. He is distinguished in many ways, in particular in his unapologetic move of cloud-level theory for cloud computing and beyond. Erik?
Thank you. What I want to talk to you today about is my journey through all kind of dimensions of duality. And this actually, for those who know, this is the cover of my PhD thesis. It's a Mondrian. And Mondrian, people often think of Mondrian about like things with lines and whatever, but he started actually painting like Dutch landscapes with gray skies and so on. And then over time he became more and more abstract. And that's very much like me. And then at the end of his life, Mondrian started to kind of, paint more like, happy things. And that's kind of, like me as well. So it's also a little bit of kind of a journey that I'm going to present to you. This is the invariant of my research career. Although I'm not a researcher, I'm a co-researcher. I used to be a researcher, but then I switched to now I'm the dual. I'm running a small product team. All right. So I don't know if everybody here knows category theory. You're all good researchers, so you should know this. But if you don't know category theory, it doesn't matter. I will explain everything, and I'm an amateur category theorist anyway. So the thing what I like about category theory is that it's very much like functional programming. So I can pretend that I'm doing theory when I'm just doing functional programming. It's like just functional programming where you use function composition only. And so it's quite easy. But then the best thing, and Dan there is also Dutch, and he told me that he's now doing category theory too. But this is why it really appeals to Dutch people, because of this thing, duality. Okay? Because duality gives you buy one, get one free. So you define something, you prove something, and then you get, something for free. Hey, Basim. But besides that, the thing that, what I want to talk about today is not about saving money, by doing one theorem and getting the other one for free. What it really gives you is that you get unexpected insights. And even if you know the duality, as I will see, is like, just understanding what these relationships are and what they imply is a very interesting thing, where the answers are not always obvious. I won't talk about adjoints today or anything really complicated. Okay, well, my first contact with category theory and with duality was way back when I worked on my thesis. That's why I had the cover up there. And that had to do with initial algebras versus final co-algebras. What we did at that time, this was the mid-80s, we were working on something called Bird-Meertens formalism, Richard Bird and Lambert Meertens. And it was a very stylized way of doing functional programming. And it started out, everybody should know or should read this. It's called the theory of lists, which is a calculus for calculating programs via, manipulation, programs over lists. And while we were working on that, we thought, this should not only work for lists, because we're doing very stylized things. We're writing recursive functions over these lists, or we're writing functions that kind of, in a very recursive way or co-recursive way, generate lists. And we're computing the composition of functions over lists. But that should work on any type. And the way you kind of discover how that works is you look at these functions over lists, and I've drawn here a attempt of a picture of a list. So this is a list. There's the empty list, and then you cons, a value on the list, and so on. So that list is built up recursively. And now there's two things that you can do with this list. You can destroy the list, and I like that. and the polite name is fold. So what you do is you replace the empty list by 0, and then you replace the constructor by addition, and now you kind of collapse that whole list into a number. And that function, you can imagine, you can define that by recursion or induction over the structure of the list. And that is what most people do when they write functions over lists. Sounds pretty trivial, but it's quite, the theory is quite rich, and it's quite beautiful, actually. And the other thing is what attracted me there originally is when you do long division, it looks like you're doing magic, but you don't have to think. You're just doing an algorithm. And programming in this squiggle style is the same thing. You can turn off your mind and just go and manipulate symbols, and out comes something, and then, oh, that looks interesting. You write a paper about it. You can go to a conference in a nice place. So that was a good life. Now, the other thing, the dual of this, is that you can create a list. And the way you do that is by having a little state machine that has 2 states, and when it stays in this state, it outputs a number, and that is the number that you're going to put in your list. And then at some point it goes to a final state, and that's when your list stops. So you can kind of generate this list via a little state machine, and that is called unfold. People that use Haskell know that most of the time you're doing folds, and very, very seldomly you do unfolds. And most people don't even know unfold. But as we will see, they are dual. But this is kind of another interesting thing, is that often there's things that are dual, where one side of the duality feels very natural and you use a lot, and then the other side of the duality feels like a little bit weird, and it's like unnatural. But maybe that's another duality between natural and unnatural. I don't know. So this is Mr. Bird, Richard Bird, one of my heroes from when I was a young Erik. And this is one of the theorems that we were using. This is called Bird's homomorphism lemma. I always kind of dream that there's a law named or an algorithm named after me, but maybe that time will come. Bird's first homomorphism lemma, which says that any function that takes a list and computes some value is a homomorphism if and only if I can, decompose that function into a map followed by a reduce. And then both of these functions, map and reduce, are both these inductive functions. They are both folds. And once you do this, you can, write your algorithms like this, and if you have 2 maps, you can compose them and so on. So there's a very beautiful theory there, and that's called the theory of lists. If you haven't read that, it's very lightweight reading. I can recommend that to everybody. So I'm going to push Bird's homomorphism lemma on your stack, and then at the end of the talk, hopefully we will get at the right stack depth when we have popped off everything else and come back to this. Now, as I said, this homomorphism lemma, you can ask yourself, is there a similar law when you're writing a homomorphic function over trees? Or, maybe over some other data structure, like a n-ary tree or whatever arbitrary algebraic data structure. And it turns out that is the case when you're modeling your data types as initial algebras. And this is the first time that I found a mathematical theory that really, abstracted the essence of what you do in programming. And the idea is as follows. You define the shape of your data type using a functor, and then you take the fixed point of that functor, and then, you get a initial algebra. Now, the nice thing here is that, if you flip all the arrows, now you get final coalgebras, where you take the greatest fixed point. And you get the same thing, but then in the dual. A lot of stuff that we did in the Burt-Meertens formalism, we worked in the category of sets. And if you do that, then the initial algebras and the final co-algebras are separate. The initial algebras are all the finite data types. So if you look at lists, they're all the finite lists. And if you take the final co-algebras, you get only the infinite lists. But the types are different. So they are in different categories. A nice thing is if you look at Haskell, everybody that has done Haskell there, a list can be finite or infinite. And the beauty of Haskell is that in Haskell, which lives in the category of CPOs, initial algebras and final co-algebras coincide. So they are the same thing. And that gives you a lot of power. And here's the picture. If you're doing category theory, you always have to have commuting diagrams. So let's look at an algebra here. So an algebra is something that takes an f of something to something, okay? Where the f is the functor, and here I've just unfolded the functor. So this says I have either a pair of numbers, and I map that to a number, or I have, the unit type, and a value of the unit type, and I map that to a number. So that really gives you the structure of a list of integers, where this is the empty list, and this is the element of the list, and this is the rest of the list. And then here you see that signature for lists. So a list is either empty, or it's cons on top of another list. And if I apply the constructor, I get the list. And if I apply the destructor, I get, I take a list and I can split that up. And if you're in CPO, then, the final, the initial algebra and the final co-algebra coincide, and then you can go with the constructor and a destructor between these two. And there you see that if I have a co-algebra, that goes the opposite direction. So there you start with A, and you go to f of A. And in this case, you start with a number, and you go to either one or a pair of numbers. And now you can define a homomorphism from the initial algebra to some other one, where this diagram commutes. And we use these banana brackets for that. And this is called a catamorphism. And if you look up in your Greek dictionary, that means downwards, because you're kind of, chugging on that list and breaking it up. And then if you reverse the arrows, they point the same direction, but you see here that it goes now to the final co-algebra. And then you switch the brackets here. You get lenses, and they are called anamorphisms, which means upwards. And that is the thing, the unfold, that creates the list. Okay, so from a number, I can create a list. How can I do that? By taking that number, splitting that into two numbers, recursively generating a list from that second number, and then consing that thing back into the list. So there you see the kind of recursive unfold. And here you see I can reduce a list to a number by breaking that list into the head and the tail, recursively applying that catamorphism to the list, and then applying that the function of the fold. So it's what these diagrams show you is really a simple recursive function that follows the structure of that's defined by induction over the structure of that list. And this will then apply to every functor, to functors that have certain structure. Okay, now here's an interesting thing, and this will come up again and again. If you look at this category of CPOs where initial algebras and final co-algebras coincide, so this is not even an isomorphism, they're the same, but the thing that kind of, connects them is this notion of undefined or non-termination. So if you take a initial algebra and you want to kind of, turn that into a final co-algebra, what happens is that you introduce non-termination because you're going from something finite to something infinite. And if you go here from from this side to that side, you have to remove non-termination. So non-termination is some kind of magic energy that is involved in, binding these two concepts. And that's something, I don't know where that comes from or how you can explain it from the duality, but we'll see another example of this kind of, strange energy that binds these two dualities together. Okay, now, what do we get? I said, we want to define all these kind of laws like the homomorphism lemma in this more abstract form. And here are two laws. So this says that if I have a catamorphism and I compose that with some function, I get a new catamorphism provided that this function is a homomorphism over that guy. So when I compose it with this thing, it's the same as that thing, but then post-applied with f applied to the functor. So operationally, it's kind of, I can push f. I can compose these two guys if I can push f through this thing and then up to the recursive occurrences of the value of the inductive type. And here's the buy one get one free. You prove this one. This one follows from the fact that it's that this guy is like the homomorphism, unique homomorphism from the initial algebra. But I just reverse all the arrows. I flip everything, and then I get the corresponding law for the anamorphisms. I think that's beautiful. And these are things that, if I was brave enough, I would have these tattooed on my both arms. Now, what is this good for? You can say, Erik, this is, you're just doing some, math and blah, 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 and trying to impress your friends and families that you can do symbol shuffling. But no, let's look at denotational semantics. That's kind of a lost art. People don't do denotational semantics these days very much anymore, but I love it. So denotational semantics, what do you have there? Well, you have an abstract syntax tree, which is an inductive data type, so you can define that as a fixed point of a functor. And then what people say, I need to now define a compositional semantics. For example, if I have here expression, I need to define this function that's compositional, which means that it's inductively defined over the structure of my abstract syntax tree. Oh, that was exactly what we just did with these catamorphisms. So instead of writing my semantic functions with strange brackets like this, I can write it with other strange brackets like that. And now I don't have to do the recursion. So I don't have to write this thing, do it recursively. I just have to say, whenever you see this guy, replace it by plus, and whenever you see this guy, replace that by itself. So you've kind of factored out the recursion in this definition for once and for all, and you only tell by what you replace the constructors of the abstract syntax tree. So it's also very lazy. I like that. You factored out the recursive part, and you only have to express the things that are unique to this thing. So instead of writing the function like this, you would write it as a catamorphism like that. And now we can do something, because what you often want to do when you're doing denotational semantics, you start with, say, a direct semantics, and you want to, transform that into a continuation semantics. And maybe you want to take that continuation semantics and transform it into some other semantics. What people often do is they define the direct semantics and the continuation semantics and then try to prove that somehow they're equal. I'm not going to do that. What I'm going to do is I'm going to start with the direct semantics. I'm going to define a function that takes the semantic domain of the direct semantics and turn that into the semantics domain of the continuation semantics. And then I'm going to try to show that I can push that f over the operations that I kind of replacing the abstract syntax tree with. And then I infer, or I just calculate what this guy is, and then I get my continuation semantics. So again, I only have to come up with this f, and then I go and I crank the handle, and out comes my continuation semantics. I love that. I don't have to think again. I don't like to think. I just want to think once and then pull the crank. So, and this is where all the magic is. In the Dutch computer scientists, from the Dijkstra school always say this is where you pull the rabbit out of the hat. So I started out, the semantic domain of my direct semantics was numbers, right? I mapped expressions to numbers. So now what I'm going to do is I'm mapping that number to a continuation, which is something, and you type in Google or Bing continuation, and then you get this type. So it's like n, arrow, n. And so I need to define this function, which takes a number and a continuation of type n, arrow, n, and I need to find something of type n. Ooh, that's hard. Ah! And that can only be this application. Okay, now let's see. So what I have to do now is I've unfolded that fusion law now in the recursive form. What I need to do is I need to take this composition here of f and the semantic function and push that thing here to this place and that place, and then find some new operator here. Right, that's kind of what I'm trying to do. And the way you do that is you're just applying E. I get this. I'm applying the definition of f. Now, I'm inferring, I'm unfolding that this is the definition of f here, and I do that a second time, and I get this. Okay? So I've just pushed that f through the recursive structure, and then inferred all these lambda terms that make that work. And then I'm done. So this is a very different way of deriving semantics. And then for the numbers, that is simple. Now, you can say, but Erik, denotational semantics, that's so last century. We want to do operational semantics. Well, guess what? Operational semantics is dual to continuation semantics and of denotational semantics. And the denotational semantics was this fault or catamorphism. Guess what? An operational semantics you can describe with one of those anamorphisms. Isn't that beautiful? So here's a small step semantics for expressions. You do that by giving these kind of strange rules. For example, if I have a plus b, I can make a step here. I can reduce a to c, and then I can go from a plus b to c plus b. Or I can reduce b here to c, and then do that here. If I have reduced these things to two numbers, I can add them up. And if I have a number, that's already its value. All right, and then what you can do is you can take these derivation sequences. So I can start with an expression, and I can say, well, I'm applying that rule here, so that reduces to this, and then in the end I end up at 10. Or I can start by reducing this, and then that, and then I also end up at 10. So really, what these rules define is a tree of expressions where at every node of the tree there are branches that pick where I'm going to reduce part of that expression. So it's like an evaluation tree defined by those rules. Okay? And so the operational semantics generates that tree. And that's where we apply our knowledge, because we know how to generate a tree by doing an unfold. So if I define my tree like this, again, recursive type, tree of A, is a node of A and a list of tree of A. Now what is the unfold for that? Well, I need two functions, and starting with a B, I can generate a tree of A's if I have a function, f, that goes from a B to A, that I will use to create the node. And if I have a function G, that takes a B and returns in the list of B, that I can then use to recursively generate the rest of the tree. Okay, so this is a tree generator function, and I write this using these weird lenses. But you can see if you look at this thing, that this is exactly following that recursive unfolding based on the structure of this guy, where it's either, it's an A and a list of trees, and that's where the map here comes from, because there's a list recursively. I have to apply this thing to a list of values. All right, so I can now define my operational semantics as a function, this unfold, that takes an expression and returns a tree of expressions, which is like the evaluation tree. And if you look at here, you see steps of n is the singleton list of n, which exactly corresponds to that rule. Okay. If I have n plus m, where these are numbers, I just add them up. And then this one looks kind of funky, but if I have a plus b, I have two choices. I could reduce a and then plug that in here, or I can reduce b and plug it in there, which is exactly these two rules, right? They have the same value here, so that gives me kind of two ways to continue that tree. All right? So now we've seen that the operational semantics and the denotational semantics are defined using folds and unfolds. And then another thing that theoreticians like to do is to prove that the operational semantics is the same as the denotational semantics, and you can then try to prove that these functions are the same. So that I won't do that, but that's the kind of next exercise. Okay, so we did all this, and then that wasn't enough, because this guy here, it's an old picture from him. Okay, look at that. Does he look scary? Oh yeah, that's Phil Wattler when he was young. It's like one big ball of hair. And he was the guy that brought monads from category theory in the functional programming world. And then, of course, monads are something. There's a dual, which are comonads. And just like these catamorphisms and anamorphisms, monads are very natural. Depends on who you talk to. I think there's still a lot of people that monads, is that some kind of disease? But comonads are definitely not very, very much used. But I will give you a surprise that actually Microsoft ships comonads. And Dan Leijen here worked on it. So he is kind of responsible for making comonads more popular than monads in Haskell. Let's see what that is. So maybe I should put, Dan's picture here. If you go to Wikipedia and you look up monads, and then it's like, oh, monads is Kleisli triples, and it's like, again with functors, and very complicated. But fortunately, it's not that complicated. Monads are really, really trivial. If you look at it from a programming point of view, monads are just an abstract interface for collections. So if you ask, if I ask my 16-year-old son, how would you define a collection? What is a collection? What is the essence of a collection? He would invent monads. So what he would say, Dad, in order for something to be a collection, I have to take a value and make it into a collection that has that one value. Son, good job. And then he would say, if I have a collection of collections, I want to just, forget the inner collectionness and just kind of, dump them all into that collection. I would say, yes, son, that sounds reasonable. And then I want to be able to, transform all the elements in the collection. I say, yeah, that's a functor. And it's monads. That's all there is to monads. It's just this abstraction, an interface for collections. And now this suddenly gives this enormous richness where I can now write or reason about any kind of collection as long as it's built from these operators. And I think that's quite beautiful. And then, if you turn this into Greek, they use the functor, this is the join, and this is the unit. And there, these have to be natural transformations. Some laws have to hold. But usually, as programmers, we kind of put those under the carpet. And it's just this interface. Now, there's an interesting thing here. In Haskell, you can make functions polymorphic over types and type constructors. Because this thing here, these operators here, are polymorphic in both M and A and B. Okay? Unfortunately, C# is not powerful enough. In C# generics, you can only abstract over type parameters, but not over type constructors. And I always say that this is maybe because in ML you cannot do that either. And our friends from MSR that built generics into C#, which is, I think, awesome, but they came from an ML background, so they didn't, know that that was so useful to have parameterization over type constructors as well. And so, if you want to do monads in these other languages, you have to use some kind of pattern because you cannot really abstract over that type constructor. Haskell is a quite unique language in that sense. Now, where can we find monads in the wild? And this one is a little bit, maybe not mathematically pure, but if you look at invocation in C#, you're really doing monadic bind. Because when you do an invocation, in C#, the one way, I should kind of back off a little bit, in Haskell, monads came into being because we needed a way to talk about impure functions, functions with side effects. Okay, and one way to look at an impure function is as a function that returns a collection of results. My favorite example is a watch. If you look at my watch, it's not, your watch is not something that gives you a date time. It gives you a collection of date times. Every time you look at your watch, you kind of, pull out the next value out of it. So a side effect in computation corresponds very closely to a collection, where you kind of, every time you evaluate it, you get another value out of it. And in C#, they have picked one particular effect, and then they are silent about it. So that's here written in gray so that you can see it a little bit. But they have kind of fixed one side effect, one monad, that's the C# monad. And that's kind of, then you don't have to talk about that. But if you look at the invocation of a delegate, say, a delegate takes a value of type A and returns something of type B, but it can have side effects in computing that result. And then it will take an argument, but it will compute the argument when it's calling that function. So there can be side effects when you evaluate the argument, but when you pass it here, you pass it as a value. And then the result of applying that thing is something that has side effects. Okay, so this is really the signature of invocation, of delegate invocation. So if I have a delegate here, which takes an A, and does some side effect and then returns me a B, for example here. Now when I invoke that function, and this is really what the delegate does, you write foo of A, but really under the covers it doesn't invoke. It evaluates the argument, which produces some side effects. It gets the value, passes it to the function, or I shouldn't call that a function, because it's not pure, and then it returns a value with a side effect. So monads, everybody's using monads when they use C#. Whenever you do a method invocation, you're using monadic bind. And then, again, I'm pushing this on the stack. If you look at monads and you can then define a syntax on top of these monadic operators, and that's called monad comprehensions. And link is nothing more than syntactic sugar for monadic expressions. There's one little catch, that instead of bind, which would go from M of A to M of B to M of B, C# uses this weird, I call that the weird select many, which has type M of A to M of B, and then you get A cross B to C, and then it gives you an M of C. And if you know a little bit of category theory, this is like, sometimes people call this like strength or something. So it's like you're doing some post-processing over this guy with each value here. This is like a weird select many that C# uses. But you can define this one in terms of the normal select many and a select or a map. So it's not super new, or it's not really going outside monads, but it is a different primitive. All right, now, since we're doing duality, let's just flip all the arrows. Okay, so the other one worked quite naturally for multiple things. So I asked my son, show me what a collection is. And now I'm going to mechanically reverse the arrows. And now what do I get? Well, I get something that from this cloud of values extracts one. Somehow I have some cloud of values and it introduces some structure in here. I don't know how, for example, if there's multiple values there, which one does it pick? Or here, how does it decide where to put things? And then, the map, that's the same. Because that was not part of the monad definition, that was just because I wanted, this thing to be a functor. So now you see here, for these comonads, which we have found here, that naturally works if there's only one value in each cloud. And I think that's one of the reasons that comonads are not very popular, because if you have multiple ones, you always have to kind of, somehow still have some chosen one, because you need to know, which one to pick, or here you need to know how to, partition that guys into this thing. But if you have one, that's very natural, because then I can pick the one. If there's one here, I just create a new cloud with one in there, and then the map is simple. And so if you look at the math, this is the comonad, so they use different symbols here. So it has this extraction, and it has this thing here that duplicates, and then there's just the map. And again, there's the same conditions. Now, if you look at the TPL, and you look at continue with, and result, that's exactly the kind of cobind of a comonad. Because if you look at the bind, that would go from B to from A to M of B, but this goes from task of A to B. Okay? And it satisfies all the laws, and there's even the extraction. If I have a task, I can grab the value. So, C# or .NET Framework has comonads. Did you know that? You can go home and tell your, whatever your friends, yes, I work for a company that ships comonads. I don't think Anders knows this. Probably he doesn't want to know, because the marketing guys might be scared, we're doing comonads. But actually, in C# 5.0, they're adding support for comonad comprehensions. And that's the await statement. So when you do the await statement, that takes a task and extracts a value from that, and then you can do something with it, and then you get back a task. So it kind of corresponds exactly to, it compiles under the covers, this compiles to a continue with.
But it's always apply, right? Continue with. Oh, you go to the task of B, that's right.
Yes. Dan, you should know.
Yeah.
I think it's quite beautiful that we have this language called C# that everybody thinks is like super practical, and normal people use that. And it has monads and comonads and special syntax to help that. Wow, so there must be something really deep in this category theory stuff that people just stumble it by accident, not even knowing it. So that's I think that's super, super beautiful. All right. Next one is SQL is dual to NoSQL. Hence, NoSQL is CoSQL. Okay, so that's my kind of latest insight. There's this whole hype about NoSQL, and if you go to Building 35 and you say NoSQL, people go, oh, it's like the devil, they start to sweat, and it's NoSQL, oh. But really, it's not that scary. It's just a dual of SQL. And we have seen that, these play nice with each other, so we don't have to be scared. It's just like our friend. NoSQL is the friend of SQL. Just like denotational semantics is the friend of operational semantics, and monads is the friend of, link is the friend of await, and it's like a beautiful family. So this is Mr. Cott, the guy that made SQL popular. And let's see what we can teach him. Okay, so what we're going to do is we're going to look at the SQL data model, which is foreign key primary key stores. And when people talk about NoSQL, they always talk about key value stores. That's the most popular NoSQL store. NoSQL is kind of a little bit ill-defined, but I'm now going to define it really precisely as key value stores. And what I'm going to show is that key value stores are exactly the dual of foreign key primary key stores. So let's see what the practitioners have to say about that. So entity data model, a lot of smart people worked on that. It's a fundamental building block for describing the structure of data. But this is kind of strange, because it says it's a fundamental building block for describing the structure of data, but each thing must have a unique key. And it must live within an entity set. Now, the thing is, when I define types in C#, they don't have a unique key, and they don't have to live in an entity set. So this is a great data model, but it's not, a universal data model, because, if I write code, none of my types has a unique key. Okay? Because why is that? Because my objects have object identity, which is defined outside the object. Okay? So there must be some other kind of data type in the universe, because not every data type has this unique key. If you're a SQL guy or girl, then this makes sense, because in SQL, if you don't have a primary key in your row, you cannot even find it. But so this is a very SQL data model, and I'll make this more precise. Now the other hip kits, the new hip kits, is Rastafarians. I mean, if I would have long hair, I would have dreadlocks, and I don't know, I would probably smoke weed, or like rest. Okay, but if you look at the definition of rest, what that says is that blah 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 blah. Resources are identified, for example, using URIs. The resources themselves are separate from the representation that are returned, and it could be many things. So if you reflect a little bit on this, what they say is that things that they call resources have an address, they have a key, but when I get back the value, I get back some representation of the value that does not contain the key, because the key and the value are separate. Okay, and that's the whole idea of the web too. I mean, I have a URI, I go there, I get back a web page, but once I have that web page, I don't know where it came from, because I just get back the value. So that's a very different kind of data model, because here I have like pointers to values, but the values themselves don't have a unique key. So let's make it a little bit more concrete. This is a slide that I stole from a different talk that only talks about this. So here is a sample that's again then stolen from Amazon SimpleDB. So here I define a class, and notice that this is not an entity according to the entity data model, because there's no unique key. Okay, there's just a class. And then I can define a collection of these things, but I can put the same product in multiple collections. It doesn't have to be unique per collection. So this is very, very different. This data model is completely different from the entity data model. And then using the super powerful link comprehensions, monads, I can query over these things. And I started out with this graph. And after I do the query, I get this graph. And again, you see here that this collection of keywords and that collection of keywords is kind of shared here. So this is like a graph that has pointers kind of everywhere, instead of being values that live in different tables. Now, if I define this thing in the entity data model or in the SQL data model, you see that every... I first have to kind of normalize it into 3 types, and each of them have a unique ID here, and that ID is unique within the collection of things that this thing lives in, and you insert them here. So you see here, this is a very, very different data model. Here, things have keys, and, things are, they're not nested, but instead, they are related by foreign primary key relationships. So this is my book, and each book had keywords, but these keywords are not nested in this book. No, instead, this thing here says, I belong to this book. And this keyword belongs to that book, and that rating belongs to this book. So the arrows here are from the foreign keys to the primary keys. So they kind of go in the opposite direction. And each thing here has the ID as part of the value. And so completely different. And when I do the query, in this case, I get back something here that, interestingly enough, has no sharing. So I get this repetition here of these titles, whereas in the object world, these were shared. I had still that same collection of titles. Now I'm going to make one simplification, because here, this collection here I modeled as an object itself. And what I'm going to do is I'm just going to insert that object kind of in here. Okay, I'm going to make that value-based. And when I do that, and I should do that in this picture actually here, I'm going to compare these pictures. I'm going to inline those things in there. So it's like I have an inline array. And then I look at the pictures. And what you see is that really 2 things. The arrows are reversed. It's exactly the same structure, right? There's three boxes with arrows between them, but the arrows go the opposite direction. And then the second thing that's different is that these guys have their identity as part of the values, where these guys have the identity is not part of the value, but the identity is determined by the pointer, their address. So the identity is external, and here the identity is internal, which sounds very dual as well. So the key value store here is dual to foreign key, primary key. Now you can say, why, Erik, why is this a key value store? Well, in C#, it's not so clear. But if you program in C, when you write star P, the P is a pointer, which is a key, and you have to go into memory and to look it up. And then what you get back is the value that is pointed to by this address. So the normal memory that we know from C and from C# is a key value store. And so this is the big difference. In a key value store, parents point to their children. So the parents contain the addresses or the keys of their children. And in a foreign key primary key store, in a SQL store, the children point to their parents. Okay, because there's a foreign key from the children to the parent. And if you have a one-to-many relationship, you see that most clearly. There's many things that point to the primary key, or I have a collection of things that point to children. Good. And if you now go back to my previous examples, you see here an entity that has something that has a primary key, and then there's an association that goes that direction. And here in the NoSQL data model, you have an address that points to a value, and then that value can contain addresses that point to other values and so on. if you model this precisely using categories, you will see that this is exactly the dual. So Gavin Bierman, who is a real researcher in Cambridge, is helping me with this because I'm just an amateur and a faux category theorist. That's what I am. But Gavin, knows his chops, and he thinks that it all sound. So I must trust him. All right. Now the thing is that I'm in SQL. I'm in Building 35, and BASIM knows that. And there, the world is all relational databases. But I think the real world is all key value stores, really. Let's go to the good old core memory. Okay? That's not a foreign key primary key store. No, that's a key value store. Right? Because you have a resource or an address, and then you read the value from that thing, and it comes out. But once you get the value, it doesn't know anymore at which address it lived. So, right from the beginning, our beautiful computers were key value stores. And this is the C example. And if you, really look at what the C memory model gives you, well, I can write some word at a certain address, or I can read, a number of bytes from a certain address. And even in C, you can use the keys as values and do address arithmetic, so you can kind of walk along your memory. So it's like a kind of pimped up key value store, because the keys are not separate, but they are next to each other. Yep.
Just trying to get my head around what you said earlier. If in a relational database I give you a row,
yep,
and it contains a primary key,
yep,
without giving you awareness of the schema, of the context, you don't know that key is the key.
Very good. Really good. So you're smart. I measure the smartness of questions, how many slides ahead they are. So this is in a future slide. So good job. Because that's one of the consequences of this duality, actually. The thing is, the point I want to make is that people keep trying to come up with this universal data model, some data model that will kind of, if you just map your data into this data model, every problem will be solved. What I've tried to show here, that there is no universal data model, because there's two completely different models, and both of them appear in the wild, but they are dual. So neither of them is better. So we should not try to pick a universal data model. And instead, we should embrace both of them. And so the guys in Building 35 should say, hey, this co-SQL thing is not a threat. It's an ability, a chance to duplicate our revenue, to go from 3 billion to 6 billion, because they are dual. But they have not listened yet to me. There's $3 billion that they're leaving on the table. And, category tells them how to get that. So maybe, hopefully they will see the light soon. Okay, you asked a question about, how do I know when I get the value, what is the key? Well, that is a consequence, is that in the SQL model, your values must be typed enough to know what the primary and the foreign keys are. Okay? So in some sense, when you're doing a SQL store, you're forced to a certain level of typing. And this is something that a lot of people don't like for whatever reason. Maybe it's fashion. Oh, we all like dynamic languages. Or maybe people are lazy, or it's costly to do that. But in a SQL store, you're forced to do a certain level of typing. In a NoSQL store, you don't need to type anything, because both the keys and the values can be opaque. And that's what the NoSQL people love so much, because they can just store whatever behind that key, and they don't need to think about schema. It's all up to the person that receives the value to interpret that. So I think this follows from this duality, but it's a very, very powerful thing. Why NoSQL is so popular? Because you don't need schema. Whereas in SQL, you do need schema enough to find where the keys are.
Yeah, so the reason I asked the question is because in one of your previous slides, you made explicit that is the difference between REST, for example, where you have the URI and the representation, and then the entity model where you need to have the key. With what you just said, I think they look to me the same, because a row in a relational database plus schema is no different from the context of interaction with a web resource. I have the URI and I ask for the representation. The context now tells me which one is the key and which one is the value.
Yes, but that's the context, whereas in the relational world, that key is part of the value. If I give you the representation without telling you the URI, you have no way to know that.
And in the same way, if I give you a row from a relational database without the relational model that identifies something as a private, without the schema, then you have no way of telling.
Yes, but then I would say then it's not a row anymore. But the representation is still a representation.
Okay.
So here's I don't know what, I have till 5, right? I saw people leave, but I kind of planned to but feel free to leave, because I have time for questions. So another thing which is interesting is that there's also a duality between values and computation. So if you look at the key value store, okay, and let's look at again the interface that I had for C. This is really defined by some operation. So in order to read a key, I get back a value. Now this thing, to go back to our monad story, this thing can have arbitrary side effects. So when I read something, it can do whatever it wants. For example, it can go to the web and go somewhere and grab the value. If I look at a key value store, in order to maintain, there's something that I haven't talked about, if you want to maintain referential integrity, which means that you cannot have a foreign key that points not to a primary key, in order to check those things, these guys must be values, because if they're computations, you cannot reason about them. So there's another duality, that here you can hide the computation between the lookup and the write, whereas here they must be value-based. And this, again, is a very, very powerful thing that the NoSQL people exploit. Because when you read or when you write something, they kind of, it goes to a distributed hash table, and when you read it, so they can do arbitrary computations behind the scenes. Then there's multiple dualities, that other kind of derived dualities. If you look at the SQL data model, that already the kind of EDM document said that these things must be unique within an entity set. So you must reason about your values in a closed world. Because the rows, if I have a row that has a foreign key, it doesn't mean anything without the row that has the primary key. So you have to kind of have a closed world. Whereas, in this case, well, the only thing I know is that I need to be able to look up a key. So each key might be on a different machine and completely independent. And so you have the complete open world. Now, there's goodness here too, because if you have deep knowledge of your closed world, and this is why SQL is so popular, you can use all kind of knowledge about your tables, how they are laid out on disk, how big they are, to do query optimization. And people are super smart about that. So that's what you get from a relational database. Whereas if you do a NoSQL thing, since it's an open world, you really, as a programmer, have to decompose your query yourself, because the system cannot reason about that query in a closed world. But all these things, all the pros and cons of SQL and NoSQL just follow from this categorical categorization. And I think that's quite beautiful. All right, so let's go to the last example and look at another duality, because I've talked about monads in the abstract, and I said link is based on monads, but let's look at some particular monads. And then we see another duality. Because when I talked about these collections can be dual too. It's like when I'm the consumer of a collection, do I pull values out of that collection? Or when I'm a consumer of a collection, does the collection notify me whenever there's a new value in that collection? And that is a duality that is very interesting as well. So this is the interface that's in .NET for pool collections. So what you do is when you have a collection, you say, give me an enumerator, and that enumerator allows you to pool. You can say, move next, give me the next value. And then, once this returns true, you can get the next value. So this is a pool-based collection, and all of LINQ is defined on this. Now let's, get rid of that C# stuff and write some nice functional types. So this enumerable thing is something that takes nothing and returns an enumerator and a disposable. And an enumerator was a function that would return either a value or nothing, which when that move next returned false, or it can throw an exception. Okay? And now I'm going to simplify this a little bit here. Let's forget about all these error conditions, and let's forget about that guy and just substitute that thing in there. So really, an enumerable is a function, get enumerator, and then I have a function that I call move next to get the next value. So it's really, if they boil down the enumerator interface to the essence, it's this type. Okay, here you see that it's pool because it's kind of, it's coming out on this side. Okay, what are we going to do? Flip the arrows. So I'm flipping the arrows, and then people that recognize this say, hey, that's a continuation monad. And we've seen the continuation, right? End, arrow, end, but this is like a special version of the continuation monad. Hey, and now we're kind of working our way back. So we say, really, this thing was not only T, but it was the other things, and the sum becomes the product, and then, that thing goes like that. So I work my way back, I get that, and then, ka-ching, you get this interface, which is the interface for push-based collections. And since they're both monads, I can write queries now over streams of data, asynchronous streams. And then BaseSim is here. Stream Insight is like, a system that kind of is built on these kind of, streaming queries. They have a slightly different type, but they also expose this type to them. So again, these are two concrete examples of monads that themselves are dual. We even have callCC, because this is a continuation monad. We have a long-standing puzzle on our forum. Where is callCC? And no user has found it yet, so I'm going to reveal it here. Observable create, if you look at the type, it's callCC. But we don't call it callCC because people would be scared, so it's just observable.create. Now here's an interesting thing. These things were dual. So push collections and pull collections are dual. But just like initial algebras and final coalgebras, there is some kind of magic force that you need to kind of, connect them. So if I go from an observable to an enumerable, I have to remove concurrency. Because this thing pumps values at me asynchronously. So when somebody pulls at me, something pushes at me asynchronously, but now somebody pulls at me, that person has to block if there's no value yet. Okay, so it's like producer-consumer, so it removes concurrency in this direction. If you give me an enumerable and I need to push them, how do you do that? Well, I spin up a thread, and then I'm pushing all the values out on that thread. So that introduces concurrency. So with the coalgebra and algebra, that was non-termination, and here the magic energy is concurrency. Okay, now, since concurrency plays such an important role, we needed some way to express concurrency in our library. And so I think we reinvented what the Java people already knew, which is called scheduled executor service. We call it an iScheduler, which is really something where I can schedule work at a certain time. So this thing has a local time. And then there can be multiple things running in that scheduler. So it's like a little world that has its own notion of time. But what we also want to do is we want to be able to, when you schedule something, we want to be able to cancel it. We want to say, okay, now, abort. Well, how do we do that? If you look at our interface, you schedule work at a certain after a certain time, and then you get back a disposable that you call to kill that work. Again, if I'm now getting rid of all the noise, and I simplify it, an action is something of type unit arrow unit, disposable is of type unit arrow unit. So what the scheduler really is, it's like self-dual. You give it a function, and it gives you back its anti-function that you call to undo the damage that this thing might have done. That's also super beautiful. I don't know, this is like this, you know. So I went from all this duality, and now here's this thing. It's like all tangled together with an action and an anti-action. And then, you know, if you're a physicist, you're probably, you know, have some deep thoughts about that. But physics is too hard for me. I stick with category theory. Okay, so last 5 minutes, I'm going to circle way back to the start of my talk, to 25 years ago when I wrote my thesis. Because when I'm building a key value store, I said you have to now do this work of running this query yourself. You have to kind of algorithmically, you know, schedule that work over all the nodes where the key values, where the keys live. One way to do that that's very popular is MapReduce. Now the thing is, if you remember way back in the beginning, Bird's first homomorphism lemma really said that every homomorphism could be factored in a MapReduce. So I'm going to apply Bird's homomorphism lemma and to take my queries that are expressed as monad comprehensions and bring them into that form. But of course, since this monad comprehension is a little bit more complicated, so how am I going to do that? Well, I'm going to try to simplify. I'm going to write a continuation semantics for linked queries, where that continuation semantics brings the query into a form that I can execute on in a MapReduce style. Okay, so that's kind of my goal. So let's look at that. So let's compile linked queries into MapReduce form by doing a continuation semantics. And that needs 5 steps. I'm going to only show you one step because there's not enough time, but it will all be the same. And this is something I've not seen before. There's a lot of work, like Simon Peyton-Jones is doing work on data parallel Haskell, where they're doing something similar. The SQL guys do something similar, where they say we're turning queries into left deep joins or whatever, but it all feels to me very ad hoc. And nobody has kind of shown to do that using, that is just a continuation semantics. And this is Strachey, another one of my heroes. All papers that he wrote are recommended. And so this is what I'm going to do. I'm going to do a continuation semantics for link. And as I said, I have like 5 steps that I need to do. But the first step, what I'm going to do, is I'm going to take a query here that's arbitrarily nested. So there's a lambda in here, and you see that x is used here, and then there's a lambda here, and then x, y, and z is used here. So this is like way deep lambdas. When I'm going to execute this, you know, on a network, I don't want to have closures that are kind of deeply nested. Instead, what I want to do is I want to kind of factor this out into a pipeline, where I can do, you know, select manage one after the other. And this is, you know, what a lot of these things do. Now, instead of having a nested join, I have just like a pipelined join. All right, so, and what this really exercises is the associativity of bind, of the monadic bind. And if you write that in C# form, it is this. What it says is that if I have a nested select many, you see that has a nested here, but if that x doesn't appear there, in the G, then I can pull it out. So I can pull this guy out and move that thing to the left. So you see this X arrow F comes here, and the G, because it doesn't depend on X, I can put that there. Okay? That's just, this is one of the laws that must hold for monads. Unfortunately, C# has this weird select many. Okay? So that is a select many that has this extra functions here. So if you look at what the corresponding associativity rule for that is, now, you know, your brain starts to explode because there's so many lambdas here. And actually, I'm embarrassed. I told my boss, it took me like 3 months to do this derivation that I'm going to show you here, because you make one little mistake where you're having the binding wrong and your derivation doesn't go. So I had like literally reams and reams of paper where I was going, like, and then oh no, it doesn't work. Go back and there I had like this. I forgot to that. This X was used here, but now I have it, hopefully. And you also see that instead of this simple expressions that I used for my previous semantics, I really have here like a mutually recursive thing. I have queries, and then inside queries can be expressions, which are things that return normal values. But so that could be like a function call or whatever. But expressions can also be of collection type, and a query can also appear in an expression context. So these things are, strangely mutually recursive. So I have to do this fusion law over this complicated type using these complicated rules, and these are the semantic functions that I use. And let's look at the first one. What it really says is that given a collection Y's that has free variables X, so X is nested kind of in there, it's used in there. What I do is I do a select many on that guy with an F. And then I post-process it with F. You don't need to understand what this does, but if you look at this, it's like, I said it was a continuation semantics, but the continuation semantics usually takes the rest of the computation as an argument. Whereas here, the x's is the beginning of the computation. So it's like a co-continuation semantic. So instead of passing the rest of the computation, I give you the query that computes the free variables x. It's kind of a weird continuation semantics. And then there's this one, and then these all kind of look crazy. But here, this is the continuation semantics that I get, and this one is the most interesting one. So this is if I have a select many that has these two functions here, the weird select many, then you see here that it's a continuation. So first, I compute this guy, okay, and that one has free variables x. But what I do is I return both x and the result of that query. So this thing now returns a tuple of the result of the query and the free variables that appeared in that query. Okay? Then I'm going to compute z's, which has y as free variables and x as free variables. Okay? X and y as free variables. It computes z's. So what I'm going to return x, y, and z. So now I kind of continue with the free variables of this guy, the results of this, so the free variables of that, and then the result. And those are the free variables that are in E. Okay? So I'm just kind of passing around, all the free variables after each query, and then I can use this associativity to flatten the whole query. So it's quite beautiful. And this is the one for the other one. And here you see one of those derivations, but this one is the kind of crazy one, and after a while it's just like too many lambdas. Your brain just goes off. And then Gavin said, oh yeah, we should do this with coq. And then I was thinking, yes, but if I have to learn coq, that will take me 3 months, so I can better do it just by hand. But if there's somebody that knows coq or some theorem prover, I would love to see, if this maybe is just like one click of the button, and poor Erik has slaved on that for 3 months. Anyway, that was it. So I hope that you kind of, liked these kind of practical uses of category theory and duality. And, I think we're sitting here on $3 billion unleashed by category theory and duality. It's just now convincing the people that write the checks that that this is true. But it cannot be false because mathematicians are always right. So thank you. We have, I think, 10 minutes for questions. If people are not exhausted
Questions?
or want to go home.
Let me ask one. You mentioned querying streams.
Yes?
So there is a real question. Maybe you can solve it. So when you have finite database, then the standard query for the first order logic is canonic. What queries can they form? Now, when you have streams, nobody knows what are the natural class of queries that you ask of streams. What are the operations? Is there any naturality you can pull out?
Yes, so that is a good question. It is kind of, what is the expressive power of the queries that you can do? Well,
The right expression.
the right expressive power. So the thing is that I think we can already not answer that question for the monadic case, because if you look at the pool-based queries, they are not finite because these can be infinite as well. Plus that the query algebra that you have, this monadic algebra, I don't know how that relates to the kind of actual relation algebra, which is flat. And of course you can simulate, nested structures with flat structures, but now you go into all kind of complexity theory where my brains is too small. But I think this would be, I think it's a valid question, but I don't even know the answer for normal kind of pool-based queries.
Yeah, so your neighbors in SQL, they just take a stream, take a window, deal with this window, which is as if it is a finite piece. That's certainly not in the natural thing to do on streams.
Yes, but again, I don't know. BASIM can answer that. That also has to do with, they have a slightly different model. The stream insight model has time kind of built in, so it's a temporal model.
Right.
Whereas this model kind of, abstracts completely from time. Even in this notion of scheduler, that notion of time has nothing to do with real time. It's just, a number that, that's like it's like a partial order. That allows you to kind of express a partial order between those computations. So it's kind of a slightly different model.
It is true that we just cut it into windows.
Right,
Now it looks like a table. We can reason about it.
The slide window.
Yes, and that we don't do that in RX. There it's really streaming, and we can do windowing, but then in the windows we do like pool-based queries.
When you went from an enumerable to an observable,
Yep.
You pulled a crank and then out came the observable. But actually what came out was just the signature for it. So now in good Dutch tradition, one should consider program inversion. So have you considered that for actually producing the code for the observer?
That is a good question. So yes, so we my team guys think I'm crazy because that's what I was trying to do. It's like, hey, if I can express the sequence operators, the monad operators for the enumerable, using function composition, I should just be able to kind of flip them and get the other one. And so we tried that, but that was not successful. But we did reason about the contract, so the operational contract of these observables by, dualizing the operational contract. So we didn't manage to kind of do the implementation, but like a lot of the behavior was also kind of derived by duality. But it's a very good question. We actually tried that. They thought that I was crazy, but I said, as you say, that's the Dutch tradition, right? It's dual, so we should be able to flip the arrows. But that was a little bit, too hard because, especially in C# where it's not that easy to dualize every statement. Yeah. Other questions? Well, thank you very much.
Thank you.